Hi there, Mr. Sutton bringing you these AB Calculus 411 classwork solutions on L'Hopital's rule. For this first problem, we have the limit as x approaches -2 of this rational expression. Let's just mentally check to see what's going to happen if I plug in -2. So up here, I'm going to have 4 minus 10 plus 6, so that's a total of 0 up there. Down here, I've got 4 plus 2 minus 6, also 0. Since the limit of the numerator and the limit of the denominator are both 0, that means that I can now use L'Hopital's rule to figure this limit out. So using L'Hopital's rule, I take the derivative of the top and the bottom independently. So I've got 2x plus 5 in the numerator and 2x minus 1 in the denominator. Still have a limit as x approaches -2 of that. Let's plug in -2 again. So that's going to be, let's see here, if I plug in -2 up top, I've got -4 plus 5, which is 1. Down below, I've got -4 minus 1, which is -5. So -1/5 for my limit. For this problem, we're taking the limit as x approaches 2 of this rational expression. Now, if I plug 2 into the numerator and denominator, at least in the denominator, I very quickly see that I'm not going to get 0. So we can actually go ahead and plug in 2 for real. If I do that, I'm going to have, let's see, 4 minus 14, which is -10, plus 12 is 2. Down here I've got -1, so grand total of -2 for that limit. On this problem, I want the limit as x approaches 0 of tan of 7x and sine of 3x. Now, if I plug in 0 in both of these cases, I very quickly see that I end up with 0 and 0. So I've got the limit as x approaches 0 of tan of 7x and sine of 3x, both equaling 0. Since they both equal 0 independently, that means that I can use L'Hopital's rule. So I have to take the derivative now of the numerator and denominator. Numerator, that's going to be, let's see, secant squared of 7x times a tail of 7. Denominator, I'm going to have 3 cosine of 3x. And now let me plug in 0 again and see what happens. So in the numerator, this is really secant squared of 0, which is 1 over cosine squared of 0. Cosine of 0 is just 1. Squaring it still leaves me with 1. Dividing 1 by 1 is still 1. So altogether, the numerator is just 7. Denominator is going to be 3 times, this cosine 3 times 0 comes out to 1. So 3 on the denominator. So at the end of the day, I've got 7 over 3 for my limit. To start this problem off, let's see what happens mentally if we plug 0 in to find this limit. So 0 squared is going to be 0 in the denominator. Up here, we've got 2 times 0, which is 0. Cosine of 0 is 1. Square that, you still have 1. 1 minus 1 is 0. So we can see that the limit of the numerator and denominator, those are both 0. That means that we are allowed to use L'Hopital's rule. So let's go ahead and take some derivatives. So we'll start with the denominator. That's the easier of the two. So that'll be 2x down there. And for the numerator, we're going to have 1 getting zeroed out. We're going to have -2 cosine of 2x for the outer function, but now we have to use the chain rule. So next we have to take the derivative of cosine itself. That'll be -sine of 2x. And then we have a tail of 2 on that one. So simplifying all of that, the 2 here and this 2 can cancel out, and the negatives cancel. So I end up with 2 cosine of 2x sine of 2x over x when all is said and done. Now I can simplify this a little bit more before I take the limit, and that this will help me down the road in case I need to take another derivative, because it turns out that 2 sine of something cosine of something is really equal to sine of 2 times the something. This is one of our double angle identities. So I'm going to turn this into limit as x approaches 0 of sine of 2 times 2x, which is sine of 4x, all of that over x. And now let's go ahead and plug in 0 again. So that's going to give us 0 in the numerator and the denominator. Both of those are going to be 0. That means I can again use L'Hopital's rule. So numerator derivative, that's going to be, let's see, cosine of 4x times 4. Denominator is going to be 1, all as x approaches 0 for the limit. So we've got, let's see here, plug in 0 one more time. Cosine of 0 is 1, so we have 4 times 1 over 1, which comes out to 4. That gives us choice E. For this problem, we want the limit as x approaches 0 of f of x, where f of x is 2x squared plus 1, minus f of 0 over x squared. So let's first start by mentally plugging in 0 to see what happens. We're going to have f of 0 minus f of 0. Well, that's got to be 0. And then we have 0 squared, which is also 0. So we see that the limit of the numerator and the limit of the denominator equal 0, both of them. That means we can use L'Hopital's rule to evaluate this. So taking the derivative of the numerator, that's just going to be this expression minus all of this stuff with 0 plugged in. Now, when you plug 0 into all of this stuff, you get a constant. So that gets zeroed out when you take the derivative. So really, the numerator is just this stuff here, 2x squared plus 1. Derivative of that's going to be 4x. And then we have 2x for our lower derivative. And 4x over 2x, that's going to end up being just 2. So limit as x approaches 0 of 2 is just 2, gives us answer choice C. On this problem, we're trying to find the limit as h approaches 0 of this expression. Now, if you mentally plug 0 in, e to the 0 is 1, minus 1 is 0. In the denominator, we have 2 times 0, which is also 0. So the limit of the numerator and denominator both equal 0. That means we can use L'Hopital's rule. So we're going to take the derivative of the top and the bottom separately. Upper derivative is going to be e to the h. Lower derivative is just 2, as h approaches 0 for both of those. Plugging 0 back in, we're going to have e to the 0, which is just 1, over 2, so 1/2 ends up being our limit, choice B. On this problem, we're given a table of values for f and its first 3 derivatives, and we're also told the third derivative of the function is continuous on the interval from 0 to 4. Good to know. Let's see here. We want to know the limit of x as x approaches 2 of f of x over x minus 2 squared. All right, so the first thing to keep track of here is that the third derivative is continuous. What that means is that the other functions down here are also going to be continuous, which is important because that means that when you're trying to take a limit as x approaches 2 of these various functions and derivatives, the limit and the function value in the table will actually match up. We can't always assume that the function value and the limit are the same, but since we know the third derivative is continuous, that means all these other ones are continuous, and limits and function values are going to match up. So since third derivative is continuous, function values represent limit values. Moving on now, if we take the limit as x approaches 2 of f of x, that is going to be the function value of 0. And if we also take the limit as x approaches 2 of the denominator, that's going to be 0 squared or 0. Since the numerator and denominator are both 0, that means we can use L'Hopital's rule. So that's going to be derivative of top and the bottom, so f prime over 2 parentheses x minus 2. And the limit as x approaches 2 of f prime is also 0. Same thing for 2 times x minus 2. Since the numerator and denominator limits are both 0, we can use L'Hopital's rule, hopefully for the last time. So that'll end up being f double prime now. All of this is x approaches 2. F double prime times just, well, this is 2x minus 2, so the derivative is going to be 2. F double prime limit is 5, so we end up then with 5 over 2, which gives us choice B. On this one, we're trying to find the limit as x approaches 0 of this expression. So just mentally plugging 0 in, e to the 0 minus 1, that's going to be 1 minus 1, which is 0. So the limit of the numerator is 0. The limit of the denominator is the same thing. It's also 0. Since those are both 0, that means we can use L'Hopital's rule to evaluate this. So taking my derivatives, I've got the limit as x approaches 0 of e to the x, the derivative of the numerator, over 1, and now plugging 0 back in, we have e to the 0, which is 1, over 1, comes out to 1. Choice C. For this problem, we're trying to find the limit as x approaches infinity of this expression, where a and b are constants. So just thinking about mentally what happens if you plug infinity in here. So that's going to cause the numerator to grow without bound. Same thing with the denominator. The limits of both the numerator and denominator are going to be infinity here, because you're essentially taking the ln of infinity, which is still infinity. So we can apply L'Hopital's rule in this situation. So taking the derivative of the numerator, that's going to be
1 over bx plus 1 times a tail of b, so b over bx plus 1. Denominator derivative, that's going to be, let's see here, we're going to have 1 over ax squared plus 3 times a tail of 2ax. So 2ax over ax squared plus 3. So let's write all of that out. There was the derivative of the numerator. There was the derivative of the denominator. And I'm going to do a little same change flip action to try to simplify this before I take any more limits or derivatives. So doing that, in the numerator, I'm going to have b times ax squared plus 3 in parentheses. Denominator, I'm going to have 2ax and then parentheses bx plus 1. And just to make my life a little bit easier, I'm also going to distribute that so that I can then choose my champion on the next step. So I've got ab x squared plus 3b, and down here I've got, let's see, 2ab x squared plus 2ax. Now choosing my champion, eliminating lesser terms, ab x squared is the fastest growing term in the numerator, and then we have 2abx squared in the denominator. And then I can actually, these are the exact same thing, except this has a 1 and this has a 2, so I'm going to reduce that to just 1 over 2. And that's going to actually give me my limit. So that's going to be choice B. For this problem, we're given the derivatives of f and g and some function values of f and g at 0, and asked to find the limit as x approaches 0 of f of x over g of x. So first we start by trying to take the limit of f of x and g of x. Now it's tempting to just go ahead and say, well, since f of 0 and g of 0 are both 0, we've got 0 over 0. Got to be careful though. We can't assume that a function that we know nothing else about has limit values and function values that are the same thing. We know that these can be different things. So an additional hint they gave us here is that f prime is cosine, which is a continuous function, and g prime is 1, which is also a continuous function. Since f prime and g prime are continuous functions, that means that f is differentiable, and if it's differentiable, that means that f and g are both going to be continuous. They're both differentiable, so they're both continuous. Why do we care? Because that means the function value and the limit value at x equals 0 are in fact going to be the same thing. So you would actually have to write something about this on a free response if this were not a multiple choice question. All right, so that means that when I take the limit of f of x as x approaches 0 and of g of x as x approaches 0, these will both in fact be the function values of 0. That means I can use L'Hopital's rule. So I take the derivative of the numerator, which is just f prime of x, and the denominator, which is g prime of x, take that limit as x approaches 0. And the good news is they actually told us what f prime was. It's cosine of x. And g prime of x is 1. So this is just cosine of x over 1. Plugging 0 in, cosine of 0 is 1, so we just have 1 over 1, which is 1. Choice B.